The topics that are going to be covered in this course are logistic regression, regression diagnostics, and that one of the specific things that we're going to talk about with regression diagnostics is a term called collinearity. Have you heard that term? Did you have it in the anything about that in the biostatistics course you had last spring? Or you might have had it somewhere. We're going to talk more about that and what it means and how you address that. And then we're going to talk about survival analysis. And finally, in the last couple of weeks, we're going to talk about Poisson regression, which is a third kind of mathematical modeling technique. So for the most part in this course, we're going to be talking about different regression modeling techniques, and that's why this is called epi-modeling, epidemiologic modeling. Hopefully, by the end of the course, you're not only going to know, what these models look like, you already know something about logistic regression, but you're going to know how to work with them to be able to actually do analyses and make sense out of complicated data. So that's what we're going to cover. The two main texts for the course are texts written by myself and Mitch Klein. Mitch Klein is another faculty member in the Epidemiology and Environmental Sciences department, and these two texts are now in their third edition. And whether you buy them or not, or whether there are a couple of copies of each text on the closed reserve in the Health Sciences libraries. If you don't want to buy them, that's fine, but you're going to have to compete with anybody else who wants to borrow them. So it's better to have them, and it's up to you. And we'll talk maybe more about, there's the hard copy version and then there's the electronic copy version, which you can get either way, but there's an issue. We may say a little bit more about the electronic copy version. There are other course materials that you might want to consider, one of which you've already spent some time working with last spring in the course that was it Azhar Nizam taught it? The regression analysis course, was it? Who was it? Oh, it was Bob Lyles taught it. Okay, Bob Lyles taught it. Okay. There was that pink book. Okay, I think it was pinkish. And one of the authors was me, and another author was him. Okay?
You can't get away from us.
Well, so you can't get away from us.
Sorry.
We're surrounding you, no matter what you do. So now there are some other things to mention, which I've previously mentioned, maybe previously mentioned. One of these is a textbook that was written a long time ago, 1982, and I'm there again, because one of the things I do is I spend a lot of time writing textbooks and teaching courses, not only here, but at other places. And this was the first textbook that came out about epi methods that was sort of in the more current way of thinking about things. And then there have been other textbooks since then, one of which is by Ken Rothman. I know you've seen that one, I think, in your 530 course from last year, and was also used in the 534. But this was the first one that came out. And then one of the things that you were made aware of last spring in the 534 course was this recently developed a very unusual electronic textbook called Active Epi Web, which originally was in the form of a CD-ROM, and I converted it to the web because most computers don't even have CD drives anymore, so I had to do something. But now it's free to anyone, anywhere in the world. And at this time, right now, after I made it available about 2 months ago, there are 1,300 people that have already signed up for it in different parts of the world that are either using it to some extent. It turns out that Active Epi Web is a 21st century version of the epidemiologic research book. It's just written in a different format. It's much more fun than reading a text. So it's something that, and there are parts of Active Epi Web, as I mentioned in here, that are related to what we're going to be covering in this course. The chapter, it's actually the last chapter in Active Epi Web, is on matching. And you may remember that we talked about matching in 534. Eli talked about it matching in general, and I talked about logistic regression for match data, and that was in the last class, and I know we got a lot of comments that went pretty fast. Well, we're going to go into more detail on that here, but in the last chapter, there's all this stuff about matching. in the last chapter of Active Epi Web, and it's fun. You ought to try it if you haven't tried it. So that's another reference. And then the last thing is, when we moved from GCR to CNR about 3 or 4 years ago, I had all these papers on in actual hard copies of papers, and I decided to put them all in a computer, scan them, and put them in a library on the computer. So there's a whole library of methodologic papers that you can get from the S drive if you want to look up some topics that on any methodological topic that you're interested in, that we may mention in the class or you may be interested in otherwise. It doesn't cover everything that's been covered in the last 3 years, but there's a lot of stuff in there. Now, let me say a couple of other things here. You're going to be working with the course using Blackboard, because that's where we put everything, and you've already spent a year, most of you, almost all of you, spent a year getting used to how Blackboard works. So one of the things on Blackboard, in addition to the lecture notes, copies of including this little talk and what Eli does today, is we record all the lectures. And so you can go back, and we usually put up the recordings almost as soon as we finish the class, or as soon as we can get them up there. So you could use those recordings to review anything that's covered in the class, and it's something that you ought to consider doing. The lab slides, the slides that are actually used in the labs, are also up on Blackboard. Now, at one point we had the different labs with different folders, but now they're only in one folder, the lab slides for everybody, because everybody's using the same, all the TAs are using the same basic set of lab slides. They may do it a little differently according to the way they want to present it. And there are various reference readings and papers that we're going to suggest throughout the course that are located on Blackboard in a folder called the Additional Materials folder. And there's also data sets that we're going to be giving you for homework that it's located on Blackboard that I think they're in the assignments folder, where the assignments are, where we're going to be asking you to work with them. So that's materials on Blackboard. Homework, as you know, I think as the TAs talked about, we're not collecting homework. Class is too big to try to deal with having the TAs grade them and us deal with that. But homework's very important, and it's very important for you to do it as, when they're due, and you should probably try to write things up as if you were going to hand it in, even if you're not going to hand it in. We're going to post the answers either just before they're due. The day they're due is usually the lab, and we'll probably just post it a little bit, maybe the day before, so you'll have a chance to check on your work. And there's a homework assignment that's due tomorrow. We call it homework 0, which has to do with which just has you reviewing everything you've had up to this point in terms of biostatistics, and particularly what you've had in epidemiology up to this point in your previous year. So it's important that you try to do homework 0 if you haven't already tried, and the answers will be posted sometime tomorrow. It's not our intention to go spend lab time talking about it, because this is meant to be a review, and so that's the homework exercises. Your grades will be determined by 2 midterms and a final exam, and the final exam has 2 parts. There's an in-class part and a take-home part, and we'll talk a little bit more about these exams a little bit shortly. Computers for this course, you'll be using package programs, and the main one that we're going to be spending most of our time talking about is SAS, which is what we've been using in this school more often than any other package. But if you have another package that you're more comfortable with, like Stata or SPSS, it doesn't mean that you can't use that. It's just that our TAs and us, in some sense, are more familiar with how SAS works. But if you're more familiar with Stata, SPSS, or there's another one that's really important to know about. What's that? R. Okay, how many know about R? Have used R? A few of you have. What's nice about R? It's free, right? Right? And so that's a good reason to consider using R. And in the survival analysis book, we have a computer appendix. We also have one in the logistic regression book, but the computer appendix talks about how you can do logistic regression, or in the other book, survival analysis, how to use different packages, not just SAS, to do logistic regression or survival. In the survival analysis book, there's a section on how to use R to do survival analysis. We didn't put that in the logistic regression text. That was the third edition was done before we decided to sort of add something on R. So if you want to learn about R in a very abbreviated way and you don't know anything about it, you can look at what we've written in at least in the survival text. So that's that. The labs, which started yesterday, we'll do any one of these things listed here: review the lecture material, answer any questions, discuss the homework, discuss computer issues. So that's all I'll say about that. Now, I do want to say the last couple of things I want to say here before I'm going to let Eli, but he's left, so I guess I have to, a couple of things I want to say here is, how do you study for this course? Okay, and what I'm saying is, everybody's different. Everybody's going to do it the way they feel most comfortable for themselves. Some of you are going to be sort of better off than others in terms of having a stronger mathematical background, being more experienced in epidemiology and more experienced in and working with mathematics. So each of you are going to have you're going to make your own decision on how you do things. But if you're concerned about trying to do it as good as you can, and particularly if you're worried because you don't think you're as smart as some of the other people in the class and you have to work harder, then the best way to do that is what I've listed here. Before each lecture class, read the chapter being covered. How are you going to know what chapter is being covered? Well, I've got the syllabus, so you can look up on the syllabus what the topic is and figure out what chapter is being covered in the textbook. And you could review the lecture notes, which will be posted on Blackboard, so you can see what's going to be talked about, even though you might not understand everything, but you will understand a lot of the stuff we do in the next couple of days because it's a review. Okay, so that's the first thing. You prepare before each class. Now, some of you are just going to go in the class cold and not look at anything. If you do that, you're not going to understand things as well as if you prepare a little bit before class. And after each lecture class, I'm just saying this is the ideal thing. Not everybody's going to do this. Review the lecture notes from the class and view the recording of the lecture. That way you're going to be able to sort of go over what's been covered, and you can, with the recording, you can stop it and replay it and all that. Okay, of course, another part of this thing is we have office hours for not only Eli and myself, but the TAs have office hours. Use those office hours to talk about what's being covered from one week to the next. Don't just wait for the exam to come up to start studying. You need to study throughout the whole thing. And you need to have an approach to the homework where you try to do the homework as regularly as possible. And one thing is you might want to consider working in a small group, not just do it yourself. In some way, you have to decide how to do that. You might want to start the homework assignment for the next Wednesday lab before, way before the lab starts. You don't wait until the Tuesday to do the homework assignment. If you do that, you're going to have more problems. This is just common sense here, but some people are not going to have any problem at all. And some people, if you're worried about it, you should do what I'm suggesting here. And finish the homework assignment by the lab day, and then they'll be discussed in the lab. And as I say at the bottom, every individual is different, so this may vary from one person to another. I just want to make sure that there's an ideal way to do it. Not everybody's going to do it the same way. The lecture recordings, some people may say, well, it's being recorded, so why should I come to class? Well, that's your decision. If the room is empty, we'll still be here. I mean, I don't know. We don't know, but it's we'll be hurt, but it's really up to you. But the idea of the recordings is so you can review what's being talked about in the class, not as a way to substitute for going to the lectures. Some people go out of town, do something, and you may decide to skip a lecture for one reason or another. You might be sick. I hope not. But okay, now this is the last thing I want to say before Eli takes it. So I'm going pretty fast relative to how I've done in the past. Okay, I want to talk about the exams. Okay, Well, first of all, the midterms, there's going to be two midterms, midterms 1 and 2. The dates are there, October 1st and November something, November 2nd. These are things that you do individually, you know, and we have, I think we have 3 different classrooms where the midterms are going to be, at least 3 different classrooms, so you can spread out. And we want you to spread out. We don't want you to be sitting next to each other and looking over each other's shoulder, that's for sure. The midterms are meant to be 2 or 3 hour exams, or even less. But we want to give you time to take them. So they start at 4 o'clock, and you have until 9 o'clock to finish them. You know, some people will take every last second, you know, to do it, and other people will be done in an hour and a half or something like that. There'll be very few that do it earlier than that, and it's, you know, again, you decide how you want to do it, but we're giving you time to do it, you know, that's the way they're going to be set up. Now, one thing about you, when you're taking the midterms, you can use your notes, your class notes, your lecture notes, but what you can't use is the computer. You can use your lecture notes in some fashion, but you can't take the computer into the room. So you're going to have a hard copy of the lecture notes. You can have your homework assignments, take them in there, the hard copies of them. But we don't want people to be using the computer during these exams. So that's the main requirement. Did I miss something? The what? And which also includes cell phones. We don't want you to be in there with the cell phone calling other people sitting across the room saying, what's the answer to question 3? Okay, so you can't use your cell phone. Not that we're going to tell you not to bring them, you know, not to bring them in. Not that we're going to check you like you do at ball games or at concerts and stuff like that. We're not going to check you, but, you know, you're on your honor to do that. So that's one thing. Then there's the take-home final. Well, then it's really the final is 2 parts. There's an in-class part, which is going to be very much like the midterms. And by the way, both the midterms and the in-class part will have practice exams that you'll get, at least 1, maybe 2 practice exams that you get at least about a week before, so you see the kind of exams we've given in the past and have some practice doing them. Now, when you get these practice exams, one thing you should make sure you do is you do them. And you should do them almost as if you're taking an exam. If you do them sort of helter-skelter and don't, you know, try to do a little bit of this, a little bit of that, just look up the answers, we're not going to give you the answers right away, so you can get a chance to do them without the answers. Then we'll give you the answers a couple of days before we talk about them in the labs. But we want to give you practice doing the exams so you have an idea of the kind of exams we write. That's the in-class final. Now the take-home final is different because the take-home final is something where you're going to get a data set and a sort of a description of a research study. It's primarily very likely to be involving survival analysis because that's the last big major chunk of the course that we do. And you're going to be having to do an analysis of the data set by answering a whole bunch of questions about what's in the data set and what the research study is. Now, the reason why we give you this take-home final is because we think, and I've been teaching this course since 1993. Eli just came aboard about 2 or 3 years ago, but we've been having the same kind of take on. The reason why it's there is so that, you know, you take these other classes like Epi 530 and 534 and your other class, and they do these short answer finals, these multiple choice finals. You never really get the experience of what it's like to analyze a real data set. So that's why we give you this take home, so you have that kind of experience. And you're allowed to work in groups of up to 3 people. And one thing I should say right now, start thinking about what that group might be. I mean, you know, most of you know each other to some extent. Form a group, you know, form a group now. It might be the group that you work on for the homework assignments, okay? And that might be the same, you might switch throughout the semester and make a final decision, but at some point you're going to finalize what your group is, and then you're not going to switch groups once the exam is given out. And the take-home final will be given out at least a week before the Thanksgiving vacation, so you have about 2 or 3 weeks to work on it. Okay, So that's the main thing about the take-home final, except there's one other thing. The thing about the take-home final is I've been doing this for years, as I said, for 22, 23 years. And, we have a large class. There's 160 people in this class, okay? So to give a take-home final, which involves a whole bunch of work that you have to do and we have to grade, is not fun for either you or particularly for the instructors to have to grade. So we've tried to figure out ways that it would be easier for us to grade, easier in terms of not take the whole rest of December to grade, because we couldn't do that anyhow, because it's due in about 3 or 4 days after the exam is due. So we have certain special ways about this exam, certain special rules. For example, there are 15 questions on the exam. Typically, it could be 16 this year. And it turns out the 15th question, and this is something you have to think about now, but the 15th question is a tougher one. Okay, is a more difficult one. And the thing is, if you don't do the question 15, you have an option. If you don't choose to do question 15, you cannot get an A in the course. In order to be eligible for an A in the course, you have to do question 15. You have to earn the grade by doing something special. Okay? If you do questions 1 to 14, you can get even up to 100 points on this take-home final, but you can't get an A in the class. The highest grade you can get is a B+. We're partly doing that to sort of separate, I don't know, not really the wheat from the chaff, but somehow to make our grading sort of easier. So only the people that really want to go for an A, we're going to be focusing on in terms of looking at that question 15 and the other questions, but particularly question 15. And if you're here primarily, you don't really care that much about the A, or you're having trouble in the course in terms of the two midterms exam, and you don't think, you're probably not likely to get an A, and you don't want to spend time doing this extra question anyhow. There's enough stuff to do with the first 14 questions. You might still want to do the 14 questions and be very happy with getting a B+, or as high as a B+. So that's the take-home exam. So you might want to think about where this all, why I told you why we do it. We want to give you an experience to do that most people can't get. We want to make our life a little easier in terms of how to grade the thing. So that's why we've come up with that way of doing it. You won't get this in other classes. I don't know if you've gotten it in any class. I know Penny's class, which most of you took, she has some kind of I don't know if it's that kind of a thing exactly, but you have some exercise throughout the class, but I don't think you have this kind of a final. So it's an unusual thing. So I'm done, other than what kind of questions you have, and maybe Eli wants to say anything more about the take home or anything else that I've said.
I think the take home's fun.
Take home is fun.
Yeah, I think it's. Despite this scary grading thing, it's a really good experience to develop a report with real study data that is something different than the homeworks, and is something you may actually go back to. I think people would be referencing it later as a example of how to really work through a survival analysis, and in your workplace or further graduate work, you'll probably come back to it. I think it's helpful.
You will remember this course.
I get stopped by people in the airport, hey, I TA'd the course several years before I started teaching it, and you meet a lot of Epi 740 alums that have gone out into the world of public health, and actually this is the one course where they keep the book, and you keep the book on your shelf and you come back to it, and this is really where if you're finding yourself in an analytical capacity. After here, this is really where things kind of converge, and you're going to be yes, this is where I learned how to, X. But so I think, I'm setting the expectations a little high, but this is going to be fun.
And of course, we have to, every year is a new year, and it's up to us to try to make it work, and we hope it works for you. So, we're going to do the best we can to try to be a good experience for all of you. Any questions about anything we've said? By the way, the other thing is, as some of you know, but not Eli, I try to learn your names, okay? And what I do is
I try.
He tries, but I spend about 2 weeks prior to the first class looking at your pictures.
He goes on vacation.
I go on vacation, and I was at the beach last week, and I'm looking at your pictures.
I just don't get to go on vacation, so.
But the thing is, it's not that easy when there's 160 people to know everybody. And before we walked into the room here, I was checking to see who I could remember. I mean, I could see Casey over there because I already met you once, and I could see, I don't know, there's Daniel. Yes. Yeah, see, I got a few people, right? So I'm doing okay, but 160 people is not that easy. A lot of you have similar names, or you look alike. So, and there's at least 3 Julias in this class, and I know 3 guys. There's Kevin, there's Spencer, and there's Zachary. To me, they all look alike. And then there's the people in the class that are that all have the same kind of hair. They're Caucasian women. They're all about 24 or 22, 24. You all look alike to me, And I'm trying to remember who you are. And I look at you on the page, and I can't, if I see you, I don't know. So one thing I want to do, and Eli really wants to do that, we want to know who you are. We want to learn who you are. And we, over the course of the semester, as you see us in various places, if we don't recognize you, could you come up to us and say, hey, guess who I am? Or try to guess who I am. Or if we can't get it, tell us who you are. Okay? So I'm done. Okay?
Yeah, I think don't be a stranger. I think some of the most rewarding interactions are emails with weird questions. There are things that come up. And, so I think, or is you'll be working on your theses this year, and people will inevitably, you'll come to us or have questions or things. Yeah, so I think those kind of side interactions are really fun. So don't be a stranger.
And by the way, one other thing is, I am over 40 years older than Eli is.
Is that whose credit or just credit?
This guy is a rising star.
And you're
and I'm a
fading
star.
So you average us out and you get a functional, professor or something. But they had to give you 2 people. So we're now turn to very serious matters, which is logistic regression, but we'll still have fun with it. And I think what you'll see is that a lot of this is reviewing from 534. That's intentional. It's been a long summer. You've been overseas saving the world, or here saving the world. Some of what we ended off with 534. May seem kind of distant and hazy. And even if it's not, I think it's important to make that bridge. So you might say, hey, I've seen a lot of this before. You might feel that way today and maybe into Tuesday, but then we're going to kind of go off on our own pathway. And really, once we start talking about modeling strategy, how do you really identify the right variables and model and what makes sense, and how do you really kind of see a story in this forest of stuff? That's going to start to feel different. And then once we get to the different forms of logistic regression, we didn't really break it out on that brief summary slide, but we're going to actually talk about 3 variations of the logistic regression model, not just the binary model, but kind of other ways of thinking about the outcome. And that's going to be all new stuff too. So it's going to be less familiar as we go through this. So I'm just going to kind of take a big view of this today. This is kind of what's the contents of this lecture, starting kind of with the why are we here, what's this about again, working through the basics of the binary logistic regression model, and kind of thinking about the odds ratio, which is kind of that key measure of association, measure of effect, depending on the study, that you get out of that model. And then we'll talk about some of the statistical machinery behind it and what you might do with it in terms of how the model estimates come about, which is the process of maximum likelihood estimation, and then hypothesis testing and confidence intervals. And we'll probably barely get here today. We'll have to finish this up on Tuesday. But that's okay, we've got time. So this is old hat, but right, so what do we want to do with epidemiology, right? We want to describe the distribution of disease and the determinants of disease. That's kind of like the various definitions of epi have these two components. And they have, within those, there's different kind of purposes and things of interest that we try to do. So when we think about the distribution of disease, we're talking about very descriptive things often, surveillance, really kind of counting and describing, for lack of, simpler words. And in this situation, we're really just caring about associations mostly, right? We're talking about, the people that have this feature tend to have more or less disease, right? The people that live near the nuclear power plant tend to be more irradiated, that kind of idea. So those are associations, where we're not necessarily trying to figure out a causal small mechanism and really prove that, oh yes, it was the fact that they lived next to the plant, that is why. And if they lived in a universe where they were not living next to a nuclear power plant, they would not be irradiated, right? We're not going there, we're not doing the counterfactual thing, we're just describing. The other end, the other major kind of goal of epidemiology is to think about determinants. Why is this going on? Right, so we're thinking of etiology, we're thinking of mechanisms, and we're thinking of cause and effect. And that's this other kind of branch of epidemiology. If you think about, the different types of, careers in epidemiology, certain ones hang out mostly in here. If you're thinking about research studies, you're thinking often in determinants. If you're thinking, state health department and you're working in the surveillance branch, you're thinking perhaps up here. And then there's this third kind of aim or third thing you might want to do as an epidemiologist, which is about predicting and classifying disease. You might be developing a risk prediction model to figure out who's going to get irradiated or whatever. I'm stuck on radiation today. And in this kind of predictive world where it's kind of in between both of these, you might be thinking about associations and causes. So this is kind of the landscape of things we like to do in epidemiology. We like to describe the distribution determinants and maybe predict a little bit. The methods that we're going to do in this course are actually useful for all of these endpoints. Much of our language is going to be around the second one, which is around determining the determinants of disease. But really the modeling methods are really kind of across all three of these areas, can be used across all three of these areas. So when we think about that second bullet, around the etiologic cause and effect kind of piece, where we can break down usually the problem into these like basic components that we're trying to describe, usually a causal association or causal relationship between a health outcome and an exposure, right? And in this course, we're going to put a lot of letters and nomenclature on this. We're going to use the letters D and E for exposure and disease, which I'm sure you've seen before. So here we have a health outcome and an exposure. And to start, we're going to think of the health outcome as a binary state. You got it or you didn't get the health outcome. You're alive, you're dead. That kind of thing. And then there's some exposure, which might be also, it might be binary, it might be continuous, it might be categorical. But this is the idea. We want to ascertain this association. And the problem is that often that's really difficult to do. Without directly experimenting, we're often observing what's going on in a population through various study designs, which you know all about, and we'll come back to those. And that's difficult because often there's other stuff that gets in the way of observing this relationship. And then we have to control for those things. We have to kind of sort them out and control for these other things that get in the way. And those are going to be some control factors, and we're going to use the letters C's to represent those. So we have to kind of correct for this other stuff that gets in the way. And this is the idea of epi research, okay? So you've heard this for a year, you know this, but I'm just making sure we're all starting on the right page here. So why do we need to control for those other things? What are the types of things, how do those other things get in the way of discovering truth between our exposure and our disease? Well, this is kind of the three main reasons why we control for stuff, these other extraneous factors. The big one that I'm sure we've all spent a lot of time on is confounding, which is very, very different from the second thing, which is interaction or effect modification. Confounding is when we have this C variable has some kind of relationship with both the exposure and the disease, and if you control for it, you get a different answer than if you don't control for it. There's this other thing moving in the background that's kind of dictating how your exposure and disease are related. And I'm not going to motivate a more specific example of that. We had like a whole lecture on confounding in the spring. But just remember that these are these other things, they kind of this invisible hand, and if you don't deal with them, you're observing a spurious relationship. So that's confounding. It's very different from interaction, which is when the association itself has heterogeneity to it. It's not just like, the people that smoke always get 4 times the amount of lung cancer. There might be nuance. It might be what they smoke, for example, or it might be other things in the background. What if you have other comorbidities? What if you have other exposures? What if you live next to a power plant that's not emitting radiation, but now it's emitting smog? Other things going on in the background that might be related to your exposure and your disease that might manipulate the exposure-disease relationship. That's called interaction or effect modification. We have to, in this situation when this kind of thing is going on, we still have to control for the extraneous relationship, the extraneous factor that is, that's modifying the relationship. And then as we know, there's another term for interaction called effect modification, which is the specific situation when an exposure-disease causal relationship is being modified. Interaction is more broad, and that's more of a statistical term, whereas effect modification is more of an epi term. So I know I'm speaking a little quickly, and that's because this is review, and we have a lot we're trying to get to the logistic regression stuff, but is this too fast? Okay, mostly shaking. Okay, so I'm going to slow down when we get to like the parts where we need to slow down. I'm just trying to get us all on the same page here. So confounding, interaction, we need to deal with both, and we're going to talk about the order in which we deal with both and why. They're very, very different. And if you're feeling like today, like I feel like I'm not able to totally tease apart the differences, go home and think about it. Because that's really, really important, and I know like it can get, if you're a step away from this material for a little while, some of the nuances of when you're looking at confounding or interaction can be challenging. Go think about it, or talk to your TAs, talk to us, we'll help you out. Very, very important distinctions. Precision is this it's an other thing to think about. It's a little bit of a different issue rather than confounding or interaction. And the thing is that sometimes when you control for this other factor that may not quite be a confounder per se, it may just be like a strong predictor of the disease outcome. There's just this other variable that when you take it into account, you can actually get a more precise estimate of the relationship that you care about. And you probably saw this in your linear regression material in 591 a bit, that when you control for other things that kind of like soak up variability in the outcome, these other things that just are key determinants of the outcome, sometimes that actually really helps you get a narrower confidence interval or a more smaller p-value for other things that you care about. So sometimes the sheer fact that you're controlling for this other stuff is helpful in your statistical inference. So this is more of a statistical reason, and these are kind of epi, big picture reasons to control for things, and they're all important, and we're going to kind of build these into our regression modeling thinking in this course. So, I'm going to now jump actually to a few things that we had, a few slides that are straight out of 534, just to think about, to kind of build back up like the ways we deal with confounding. And we talked about in 534 a whole lot of different ways to deal with confounding. And in the part that I was around for, in that middle third, we talked about everything kind of but regression. And so I'm just going to kind of review what those were really, really quickly, and then we're going to jump off into regression, which is a little bit of a different trajectory. So as you know, confounding can be addressed through study design. smart study design can kind of eliminate or mitigate sources of confounding. Or you can deal with it kind of after the fact, once you've got your data, through being an amazing analyst, which you're going to all be. Or maybe you already are. So the whole idea here is that you're kind of, through the methods that you choose to apply, we're kind of like simulating counterfactuals. And this was a slide that we had in Epi 534, and it's very similar to, I'm sure, slides that you saw in Epi 591 with Dr. Howard's. That there's this idea that, you look, that what you're trying to do is look at cause and effect, and you're saying, this is the definition of a cause in this slide, that X was a cause of Y if and only if it would not have occurred had X not occurred. And what does that mean? It means Y would have occurred anyway, all other factors held equal. We talked about what that meant. Well, this all other factors held equal thing is kind of what we're doing when we address confounding. We're trying to kind of create this scenario where the exposed and the unexposed are kind of artificially held the same on all other factors, so that we can look at the only thing that's different between the exposed and the unexposed is the exposure. And then we kind of level the playing field in every other way on all the other factors that we could count and enumerate and measure, or if we do randomize, we don't even bother with that. But this idea is that we're trying to level the playing field so that we can look at the exposed and unexposed in a fair way. And the way we do that is through a whole toolbox of things. Now, we can't exactly simulate the counterfactual in the real world, because to really, really obey the theory behind this, we need like a time machine or a clone machine or something that we don't have in the 21st century to actually observe the same thing twice. Like we can't do that. So what we do is we like throw a net over a bunch of people, and we call them the cases, and we throw a net over some other people, we call them the controls, and or whatever your study design is, and we kind of look at the experience of two groups of people, and we try to say something about this underlying impossible thing that we'll never observe. So this is kind of what we do is, in reality, is we kind of grab a bunch of people and we do this thing. And we simulate the counterfactual experience through analysis. And we had these sheep. So in 534, maybe you don't remember the sheep, but here they are. And so the ideal, like we just kind of suggested, was that you have exact clones. And let's say in this situation, we want to know does exposure kill you or not kill you? I think is what we do here, because look what happens. Remember that, and then there we go. In the exposed group, 3 sheep, flip upside down, and then in the placebo group, only 1 does. And in this situation, this is an experiment that we did where we said, okay, we have 8 clones of the same exact thing, and they all get, half of them get exposed, half of them get the placebo or the unexposed, or whatever you want to call it. In this situation, you can be really, really, really sure that the observed change or the observed difference between these two groups was due to the exposure. And the reason we were sure is because they were clones and they were exactly the same in every other way, except for this thing that they got. Okay, so this is the ideal situation. But we can't do that with humans. Like we can't actually, like I said, we don't have a time machine, we don't have a clone machine, we don't have magical ways to do this kind of thinking. So we use data. And I talked about, what about twin studies? That's one way to think about this. This is even better. Not quite clones, but it's the next thing that we have access to maybe with humans. What's cool about twin studies is that you can imagine that if you look, within a pair of twins, they're kind of almost like clones in some sense. If you're a twin, you probably don't feel that way. But this is pretty good. And in this situation, you can imagine that within a matched pair of twins, they're pretty similar on all other factors, they're in most ways. And what I proposed, one way to think about confounding control was in terms of simulating a twin study. And imagine if you could, you had a bunch of twins, here they are. You split many pairs of clones, and imagine if you kind of exposed the left half here and unexposed, or gave the other treatment or whatever it is to the right half of this dashed line. This would be actually really, in the group sense, really, really similar to the sheep thing on the previous slide, because you've balanced the exposed and the unexposed on the set of confounding factors. And this actually feels kind of feasible to do with humans. Obviously, recruiting baby twins is maybe not the easiest thing or the most practical thing in all the research that you want to do in life. But this model, this ideal, is actually perhaps achievable through analytic means. And so this was the idea with confounding controllers, that we're going to kind of balance and simulate maybe a twin study or something like that to balance the confounders here. So, and like I said here, when you're comparing the experiences of the exposed and the unexposed, there should be no confounding if you did this kind of study. So I'm just going to jump through this here. One way to kind of achieve this, you can't really do a twin study always. One way to kind of achieve this ideal is through randomized controlled trials. If you randomly assign exposure to a group of people, in theory, you're going to balance the distribution of confounders between the exposed and the unexposed. So you have 100 people, and you randomly give half the exposure and the other half you don't. You're going to kind of wind up with this kind of situation. They're not going to be twins, but on the balance, they're going to be balanced. It was not the best choice there, word. But on you're going to more or less be balanced on confounders. And what we're stuck with most often as epidemiologists is this other group of stuff, which is called the observational studies. And here, we're going to kind of arrange our data through manipulations to be effectively clones analytically. An intentional manipulation of the data. And so I came up with a pictorial way of dealing with this. I'm not going to go into all of these. This is what we did last semester. And I said, well, randomization shuffles the deck, as it were, and kind of gives you this situation where you have a balancing of exposed and unexposed. They have the same confounder distribution on average. May not exactly happen, but more or less they'll be balanced. Then there was this thing called restriction that we dealt with, where you only looked at a certain type of confounders, right? Because restriction was this thing we said, we're only going to look at only going to look at 50-year-olds. So we're going to only look at 50-year-olds in southwestern Idaho, or whatever it is, because that focus lets you kind of balance they all have the same confounders. They all live in southwest Idaho. And so that eliminates confounding by geography, because you kind of narrowly zoomed in and removed the issue of confounding. That has a lot of drawbacks, which I think are obvious. Southwest Idaho may not represent everything that you want to talk about. So another thing is stratification, which we also spent time with, where you are effectively restricting a whole lot of times. You split the data up into strata, and you look at each stratum alone in isolation. You make some conclusions, you do your math, as it were, inside of the stratum, that restricted group, and then you bring it all back together. And so it's doing a restricted analysis basically a whole lot of times, and you bring it together to make one conclusion. That's hopefully an improvement over regular restriction. And we're going to come back to stratification again in this course in the conditional logistic regression model. Matching is a related concept where we're purposefully kind of making strata, in a sense, or matched groups that look the same on some features. And that's a design or an analytical tool, it could be used in both ways, to, again, balance the confounder distribution. You're kind of like playing God in some sense, and you're saying, you have this confounder, I'm going to take you have the same confounder, and I'm going to analyze you together. And that also balances the data set on the confounders. And then standardization is another variation on the theme here, where you balance, you create the exposed or unexposed, or depending on, there's different methods of standardization, but you manipulate the confounder distribution in one group to match the confounder distribution in the other group. So you say, I have this exposed group, they have a weird demographic distribution, I'm going to manipulate their demographic distribution to look like the United States, or which is direct standardization, or this indirect kind of plays that in reverse. But the idea here again is it's an intentional manipulation of confounders. Okay, so this is like a whole lot of like last year in one slide, so I'm just putting, this is the landscape of where we are outside of the world of modeling. And what's cool about what we're going to do in this course is that we're going to, in many ways, touch on all of these inside of regression, because frankly, these can all be combined with regression modeling. And we'll talk about that. We're even going to do standardization when we talk about risk ratios in the logistic model. We're going to even come back to standardization inside of logistic regression. So these all kind of exist in the tables world of Proc-Freq, and that's kind of where we were, you know, in many ways last year, and now we're going to bring it into the modeling procedures. These are my kids, and I think they have many similarities. So I thought this is actually time lagged by 4 years, but I think they look like, I don't know, I was trying to be cute. But I try to arrange them in similar, well, that I couldn't arrange, this was 4 years ago, but this is like a week ago. I try to arrange her similarly, but I think they look twin-like, but anyway, okay. So here we are, we're statistical modeling, and I threw my own kids in. Okay, so, oh yeah, right. Okay, so we're going to jump into the logistic model with an old example, or maybe old in terms of we saw this in the spring. And it was a data set about working with a methicillin-resistant Staph aureus, which is a concern. It causes various infections. It causes nasty skin infections. And it can be associated in either healthcare settings, hospital settings, or in community settings. It kind of follows different epi patterns in those different settings. And the specific example was coming from a cross-sectional study at this wonderful hospital, Grady Hospital, located on the downtown connector, which I'm sure you've all seen before. And it's an example that had 297 patients. Everyone has a staph infection. And what's of interest is whether the staph infection is additionally resistant to antibiotics, to methicillin. And so this is the example we're going to work with a little bit for a while, and it's a convenient example. We're going to have other examples, and the homework's going to have other ones as well. But this is a good jumping off point. And so in this example, the outcome is whether their infection is resistant. And here's some other measured predictors that might be of interest. Whether the person had a previous hospitalization, which is here dichotomized, whether what their age is as a continuous years variable, a dichotomous value for sex, and then whether they were recently administered antimicrobial drugs, so antibiotics, which they might develop resistance to. And so these are kind of the control variables. You have two demographic ones, and then two that are kind of like determinants of things that kind of are determinants of your current infection, exposure to the hospital environment, and then exposure to antibiotics. So two other variables that you might want to control for. So we have four variables on the right side of the equal sign, as it were, and we have our outcome of resistance. And so here's kind of like the 2x2 simplistic layout of the data. Here we have, actually it's 290. There were 297 patients. We have 292 that have complete data for this analysis on all the variables. And in these 292, we see that the people that have been exposed to our exposure we're going to consider here is previous hospitalization. The people that have been previously hospitalized, by and large, are way more likely to have their infection be resistant. So that's this 103 over 178 that proportion have MRSA compared to just 12 over 114, let's say. If you measure that with an odds ratio, I just kind of verbally said the prevalence ratio, but if you turn that into an odds ratio, you'd say, wow, almost 12, like a really strong association. Okay, and then here's the confidence interval around that as determined through the procedures we talked about last semester. Remember the Mantel-Hansel procedures, and the procedures that Lauren talked about before that before we even talked about stratified analysis. And here's the chi-square statistic that is testing the null hypothesis of there being no association, odds ratio of 1, and here we say, wow, p-value less than 0.001, there's definitely not a null association, there's something going on here, which I think you can kind of just eyeball this and say, duh. So we think there's a strong evidence of association that people that are hospitalized seem to be the ones with the resistant infection, way more likely to get resistant infection. But is there confounding, right? This is a crude, unadjusted, simple look at our data. What if there's something else going on? And then we even did this. This is still kind of rehashing things that we did in last semester. We did like a series of stratified analyses, right? You break up into many tables of the confounders your data, and you kind of do the Mantel-Hansel procedure where you are recombining pieces of those tables to get a single summary measure of association, which was called the Mantel-Hansel adjusted odds ratio. And so, whoa. So here's this first line represents kind of the result of our crude model, the unadjusted model, the crude analysis. So we didn't control for anything. And we have an odds ratio nearly of 12. And then, we controlled for different variables, and we got kind of different answers depending on what we controlled for. And if you kind of just eyeball this, it looks like you really got to control for previous antimicrobial use here, the previous antibiotics. And that seems to, once you control for it, wow, the odds ratio really changes a lot. Remember the 10% rule and all of that about confounding? Look at that, the odds ratio changes a lot, and we would have concluded that we probably needed to control for previous exposure to antimicrobial drugs. But this is a whole lot of work. Look at this. You had to run a whole bunch of things, and you have to make some decisions about all of this. And I didn't talk about this, but this is the test for interaction, the Breslow-Day test. This is a lot of information, and there's a lot of decisions and thinking that you got to do when you're doing a whole lot of stratified analyses, right? Did I need to control for all of these? What's significant? What's important? What's the right analysis to report? My boss wants the answer. Which one of these is the answer? There's issues to think about, and they really have to do with confounding, precision, interaction, kind of the three buckets of issues that I talked about earlier for control variables. And we're going to talk about that in regression, and not necessarily through the lens of stratified analysis. What variables do we control for as confounders? Which ones were the real confounders? Which ones were our effect modifiers? How do we decide what to control for? And what is the unbiased estimate of the effects, of the odds ratio? What's the right answer? What is the right answer? What is the correct odds ratio? These are the issues we're dealing with. I'm going to keep jumping forward because we've actually talked about this. We're going to talk about it more with logistic regression. So the problem is that stratified analysis is not the panacea. It's not going to solve. It's not universally a good idea. One issue with stratified analysis is that you have to categorize your predictor variables. So if you look back here, we had age as a control variable in the stratified analysis. Age was actually measured as a continuous variable, so in order to deal with it in the Mantel-Hansel procedures, you had to categorize it into age groups. Well, that's annoying because you're kind of throwing away information, or you might get a different answer if you categorize a different way, and now you don't know what to do. Maybe we could have left the data as continuous. Other problems are that the data can become sparse, and we talked a little bit about this before in the last semester, that when you start stratifying a whole lot of ways, you can get small cell sizes, which can lead to, certain procedures don't work when you have small cell sizes, and any individual stratum estimate can be really unreliable. You have to use the summary statistics. You can't really look at the pieces of your stratified analysis very well. So it's kind of annoying. And when you have many control variables, this can really blow up. If you have 10 control variables, you have to stratify effectively on all combinations of all the 10 variables. And that could be, 1,000 tables or something really irritating when you didn't necessarily need to control for everything that extensively. This is called being a fully specified analysis or a fully parameterized analysis. And we'll see a little bit of this in regression modeling, but we're going to try to avoid this. When we deal with regression models, we're less limited by these problems. We can control for things in kind of a lighter way or less. This is a very strict way to control for something, to stratify into all combinations of all your variables. That's really intense. Regression modeling lets us control for lower order interactions or lower order terms and still basically deal with the problem without making a lot of zero cells. So that's, I think, one key motivation for thinking about modeling over stratified analysis. When you have a lot more control variables, more complicated stuff, they're continuous variables, we start looking at regression. Okay, so what are we talking about? We're really talking about statistical models, and we're putting them inside of an epidemiologic setting. But this is statistical regression models. And in the most basic sense, they look kind of like this, where you have a function of some x variables that you've measured, and they're predicting a y value, the outcome. Right? That you have some mysterious machine, and you throw some x's in, and out it says you're gonna die, or with a probability of 0.7, or something like that. There's this magic function, which we're gonna put pieces on, that's gonna spit out a prediction for y. And by the way, it's not 100% accurate all the time. There's some error component. It's predicted value on average, and then the actual data diverge by some error. Right, and this, I'm sure you saw a lot of this in multiple linear regression. This is what happens on average plus some error predicts or yields what the outcome that is observed is. Another way of saying that is the expected value of y follows this function, so without the error. On average, this function details what we will observe in the universe. And so, in the binary sense, what we're really saying is that the expected value of y, when we're talking about a binary process, is the probability of the process. So, like, let's say, the probability of, let's say this is death, and the probability of death in some period of time is 0.3. Then we're saying that the expected value if you took a sample of data, on average, it would be about if you took the average of lots of zeros and ones of people who are alive and dead, you'd get to 0.3, or the probability of y. Right? We observe lots of zeros and ones, but on average, what's going on is somewhere in between 0 and 1, and that on average is the probability. And so we're going to kind of move between this idea of thinking of observing 0-1 events and thinking that it's all dictated by some probability between 0 and 1 in the background. Right? We observe coin tosses 0 and 1, but there's actually a probability of 0.5 that's dictating how you see zeros and ones. Does that make sense? Probabilities versus observed stuff, right? We're observing zeros and ones dictated by a binary probabilistic process in the background. And what we're going to do is be modeling this using data on the zeros and ones and a model that is thinking about the probability, that thing that's between the 0 and 1. So, when we think about epidemiology, we're not thinking necessarily Y's and X's. We kind of have our own nomenclature, which is disease and exposure. And so we're going to say that Y is the D, And exposure, we might say that one or several of our X variables are the exposure, and then we're going to have other things to control for. So this is maybe a way that an epidemiologist might write that concept of what the statistical model is. We're looking at the expected value of disease given exposure and some other stuff that we want to control for. And this could be control variables. This could be interaction terms between the exposure and the confounding variables, the C variables. We're going to talk about these as effect modifier terms. We're going to go into all the other ways you might think about these control variables very soon. So we're not necessarily talking about X and Y. We really care about D and E. And so, as an epidemiologist, here's like a whole laundry list of different situations that you might encounter and different regression model approaches that you might want to take. And we're actually going to cover all of these in the course. And these are really different functions, different choices of F, the different functional forms that would be appropriate given the data you've got in front of you. So here I have if you have the Y variable, the disease variable, or the outcome variable is on a continuous scale, well, then you might be looking at a linear, like weight. You might be looking at a linear regression model. You're trying to predict weight. Continuous, it's in pounds, it's in kilograms, whatever. Binary, so here, whether someone's intoxicated, yes, no. Okay, so that might be a logistic regression model, and we're going to talk about that. These two other types of logistic regression models, we're going to talk about polytomous and ordinal. Polytomous deals with a nominal or categorical variable where there's different values to it, more than two, and there are maybe just they're unordered. So tumor type ABC. There may not be rankable per se, there's just different manifestations of a tumor, and that is a different kind of outcome, and it's got more than two levels, and we're going to talk about that. There's the ordinal logistic regression, which deals with when the data might actually be, the outcome might be five levels of severity, 1 through 5. How do we deal with that? It's not continuous per se because it's only 1 through 5, and they're integers, and that's it. There's only 5 values. How do we deal with that? Ordinal regression. We're going to look at a different type of continuous outcome when it's really a time to an event occurring. And that's going to be survival analysis. Days until someone gets an STI. Let's say you did a study, you're doing, might be a therapeutic study, and you're looking at people who are at high risk for a sexually transmitted infection, and you're giving out different therapies. The outcome is the time until infection. Well, that's a little different than the linear regression situation. We're going to call it survival analysis. And then this other one is going to be, when we're looking at counts and rates, like deaths per county, let's say, that's going to be a Poisson model. So these are all different choices of F, basically, and it's going to all fit in the same nomenclature that we're talking about, the same approach. Similar approaches are going to be useful for all of these. Okay, so what's logistic regression? This was all, the model form was introduced yesterday, so I'm not going to go into a ton of detail here on the basic functional form of the logistic function. All the logistic functions all look like this, 1 over 1 plus e to the minus x. Okay, and depending on what you put in for this x, you're going to get a different kind of interesting function, and they're going to all have this general shape. It's a sigmoidal, an S shape, and it's going to look like this, and it's going to be bounded by 0 and 1. And the way you kind of get different versions of it is by varying x, what goes in this x here. So if you do x plus 5, you're going to get this thing, and it crosses 0.5 at 5, or it should. So what we're going to be doing with the binary logistic regression model is manipulating this curve through different choices of what goes in here to fit our data. Okay, so we're going to say our data, on average, kind of behaves in this way, and I'll talk about what that means. And we're going to manipulate, we're going to find the right model that finds the right shape to fit our data. Just like in linear regression, you're finding the right line for your data. Here we're going to find the right S for our data. And so here's kind of the statistical definition of the model. And the the idea here, again, with the binary logistic model is we're predicting a 0-1 outcome. And we believe that our 0-1 outcome is dictated by some underlying probability of the outcome occurring, which we're going to call P, or P of X. And the cool thing about this is that not everyone in the data is equal. They don't all have the same probability of the thing happening to them. Some people are high risk, some are low risk, some are male, some are female. Their probabilities of getting the thing, whatever it is, death, intoxication like I had before, whatever it is, their probabilities vary by their own covariates. I'm female, so my probability is higher or lower or whatever. This probability is going to be a function of things about the people. And that function is going to be this. So the whole idea is that it's a binary process conditional on stuff we know about you, like your age, your sex, whether you live next to the power plant, whatever it is going to go into this magic function that will return your specific probability of the event occurring. So that's the cool thing, is that it's not a single probability for everyone. We're going to let it vary. Okay? So, and the way we do that is with this model that's going to, for a given set of covariates, return the probability of the event occurring or not. And we're going to figure out what this function is based on data. So we're going to bring our data to the model. These are our ones and zeros in the outcome column. Here's a lot of information about the people. Find me O-proc logistic, the values of these betas that fit the data well. That's kind of the name of the game. And because I want to know the person's probability, I want to know the odds ratio for a certain situation. Okay, so we bring data on the Y, we bring a bunch of predictors, and we're modeling this expected value, this probability of the event, given those covariates, given the X's. Okay, so the O-proc logistic thing that I said is really about estimating the alpha and the betas for this model, this regression model, based on our data, and we're going to use the process of maximum likelihood estimation. So does anyone remember, what was the thing that we did in linear regression? Do you remember what that estimation process was? Least squares. I think I heard rumbles of that. Least squares. So that was the least squares method, where you were kind of, remember there's points, there's distance from the points to the line, and you're trying to minimize the squared distance to the line. That was the least squares procedure for determining coefficients. In logistic regression, we use something called maximum likelihood, which we talked a little bit about in the spring. And we're trying to find the right alpha and betas for our data. And we're going to put hats over them to represent that they're estimates of quantities that we think exist in the universe. And when we estimate them from data, we're going to use these hats over them. So what are we going to do with this exactly? What we're going to do is these things. These are the types of things that we're going to do with this model. We bring our data to the model, we estimate these alpha and beta values, and we're going to look at p-values and confidence intervals that relate to those. And what we're going to do kind of separates into the two things that I said you wanted to do with epidemiology. One is going to be about, this is really about actually this is about the third thing I had on that slide, the prediction and classification business. What you could do with this model is you can say for somebody with a given set of X, what's their risk of developing the outcome? So that's about prediction modeling. And then we're going to talk about something called ROC curves, which is a way of evaluating the predictive ability of a model. And then we're not going to talk about it in this course, but there's something called propensity scores, which also uses this approach. But the idea here is, if you make a model, you think if it's good, it actually might be able to predict the next person that comes along, it might actually be able to reasonably predict their probability of getting the outcome. The other thing is about that second purpose of epidemiology, and also kind of the first, which is about looking at associations and associations and effects. You can use the same model that gives you risks to also talk about odds ratios, risk ratios, and prevalence ratios, which is very, very useful to the epidemiologist who wants to look at mechanisms and cause and effect. So the model can do both things, and there's going to be an overlap. When we talk about risk ratios, we're going to use this idea of how the model talks about risk, and we're going to make ratios out of it. So they're not independent purposes, but the this is kind of two sets of things you're going to want to do. Predict, talk about associations. And these can all be done with this model once you fit it to your data. The model, this is one format of the model, which predicts the probability of infection, of the outcome. I'm used to talking about infections. So this is the kind of the probability form of the model. This predicts the probability of the outcome as a function of the X variables of interest, the exposure and the confounders. You can actually write the model another way, which was gone over in the lab yesterday, which is, I'm just going to put it up here because I'm going to let you look at this at home. Here's a whole lot of algebra. What I'm doing here is going from this first format of the model to the log odds version of the model, which is, this is the probability, this is of the outcome. Here's the probability over 1 minus the probability, so that's this over 1 minus itself. That's called the odds, right? That's odds, that's old news. When you do this, things conveniently cancel out, and you're left with this e to the minus alpha plus beta 1 x1 and so forth. That's what used to be down here. Now it's e to that. And you take the log of that, and then that cancels out the e, if you remember, how logs behave, the natural log, that is. And when you take that, you get a very happy linear-looking kind of function. This looks a lot like the linear regression model, which is convenient. And so when we talk about the model, it's going to often be easier to use the log odds version. It's also called the logit form. I think I even have a little box. There we go, the logit form of the model. This function, taking the log odds of something, is called, logiting it. I don't know, there's no verb, but when you logit something, it's taking the log of the odds of the thing. So we're logiting it, and that turns this form of the model into this more linearized format of the model. And so this is going to be an easy way to represent the same information as this. This takes longer to write. This takes up more space. So it's almost an easier way to do it this way. So again, it's the same thing. These are, this is, we have our outcome. We're looking at the probability of y being 1 given some, covariates. Two versions of the model, the general form here and the log odds form. So I'm going to just end on this last piece here, which is, what does this look like for like a real situation, not just algebraic stuff? And here is kind of a way to represent the analysis that we were talking about earlier with MRSA. Here the outcome variable is resistance, yes, no, MRSA status, and then here are some covariates. A simple model would just control for each of those covariates like this. Beta 1 times whether they're hospitalized, beta 2 times their age, and beta 3 times sex, and so forth. And this is what that model looks like. And we'll end here, which is what if I wanted to know the odds ratio out of this model for the odds of resistance given you're hospitalized versus you're not, the odds ratio of that. Controlling for everything else in the model, it's e to the beta 1, which I think should be all familiar to you, because things conveniently cancel out. And we're going to talk about, I guess next time, how that behaves, what the odds ratio function is and how it looks and what cancels out when, and this will make more sense on Tuesday. Okay, thank you. What?